I reworked our kind of network model in the Python CVC Casper repo to allow for a more, at least partially synchronous model. Actually, we can model an asynchronous network now. But we can model arbitrary networks and kind of peering and all sorts of interesting things to get more realistic data. That combined with the fact that our messages are now, we call it hash linked. That just means that instead of when I pass you a message, you just don't get everything because of like the justifications, you get the hashes of the justifications. So those two things combined, I think we're gonna have some pretty interesting data coming out this week, and I'll post any interesting findings into the that new channel that's up. So that's what's going on. It took me, I mean, it was a kind of semi-significant reworking of some stuff, but I think it's pretty exciting.
Yeah, it was cool. Cool stuff. Pretty small update for me. Haven't done too much because of finals, but so the two things are kind of worked on redefining the testing language, which PR is coming along, and the second thing is had a bit of a crisis with last finalized messages. So I spent some time last week just kind of exploring what like an actual ideal adversary would look like for like blockchain consensus or something. I was wondering if I could write one because I thought it'd be interesting and cool and informative. And I kind of stumbled across this like previously unknown attack, or not, I guess not really attack, but previously kind of unknown thing. But Vlad and I resolved it. So I'll give a high level overview. So pretty much the idea is, let me actually read it a bit. So let's say we have a Genesis block B, and then two blocks built on top of G. They're both built on top of G, and they're called A and B. And then all validators go to build on top of block B. And so they do a couple perfect rounds of round robin. And so essentially what we have is B technically has some finality on it. If you were to run our safety oracles, you would say, okay, B is finalized. But if we allow the validators to make a decision on A, which previously we said was fine, we kind of let them make decisions on anything for any reason. Then what they could do is they could effectively change their fork choice away from B forever. And now that all their estimates would be on top of A if they finalized A for no reason, just arbitrarily. And so essentially what we have there is we have a situation where we detected some amount of fault tolerance on top of a block, and then validators were able to switch off that block without equivocating, which is interesting. So essentially we had to add the constraint that if you change your last finalized message or last finalized block, if you change your last finalized block, then it has to be justified by your previous fork choice. And this it seems as though this is sufficient to kind of say to kind of stop this attack from happening, at least as fault tolerance is currently detected by our oracles. But anyways, that was pretty interesting. Yeah, that's it for me.
I think I understand the problem, but I'm confused as to what, in terms of a client's ability, a validator's ability to finalize anything. I mean, is finalization a part of the protocol?
Yeah. So in the case of well, yeah. I mean, in the case of like like blockchains, we need to know what a validator's last finalized block is when they make a message, because we need to be able to check their estimate, right? If we don't know their last finalized block, we can't verify that their estimate is correct because we don't know where they're starting their walk from, if that makes sense.
Right.
And so if they have to include that last finalized block in their, their message pretty much. But the issue is if they don't do that, if they don't, if they, if we don't have any rules around it, they can essentially kind of move around the tree wherever they want with no worry, which is no good.
Okay. Interesting. And can you repeat the solution one more time?
Yeah, this seems perfectly reasonable to me.
Yeah. Cool. The solution is just that if you finalize a block, if you change your last finalized block in your message, that has to be a justified move by your last block's fork choice. So the fork choice given by the justification in your last block, which kind of makes total sense, right? Like if you're gonna make a move, then like you have to have like, if you're going to make a claim, I think this block is going to be in all future chains, it probably should have to be in your current chain as well, right? So,
right. Okay, cool. Are there changes we need to make? Did you open up an issue to address that?
No, I will today though. There are some.
Yeah, essentially what you're saying is.
Sorry, go ahead. What are you saying, Greg?
I was just saying that it seems reasonable that essentially the root has to be a part of your justification chain. That's essentially what you're arguing.
Yeah. I guess it's a bit stronger than that because it's not just. Oh, sorry. Yeah, it's part of your justification chain. By justification chain, you mean fork choice of your justification. Sure. Yeah. Absolutely. Which makes total sense.
Yeah.
Cool.
Yeah, absolutely. Yeah, I mean this.
Yeah, I'll open an issue today, and kind of summarize, and post the solutions. We have to make some minor changes to the code base to be able to support kind of that, but we'll talk, I guess.
I mean, we're not even modeling. There's no equivocations in our code base, so.
Yeah, it's even stronger than that. Like our messages don't even have currently last finalized blocks for blockchain because we kind of compromised to support everything right now. But I think we could add it without too much trouble. So
yeah, I think we certainly can. All right, cool. Greg, anything this week?
Oh, yeah. He's unmuted, but I can't hear him.
Yeah, I can't hear Greg.
oh no, we lost him. He's gone.
All right.
Yeah, Nate. Has Vlad given you any updates or anything interesting?
Can you guys hear me now?
Oh
Yes.
Yep.
Yes.
Yes.
Okay, sorry, my network is a little spotty here. I'm just checking in to make sure you can still hear me.
Yep.
Now we can. Yes.
Okay, good.
We couldn't.
Okay,
before.
cool. Yeah. All right, so I'm kind of in a deep dive mode on the trace monoidal construction. So I'm going through some work by Kuka and Kissinger, which provides a nice axiomatization, so that I can basically give a translation of that over into the row calculus, so that I can kind of complete that proof that if we have a partial trace, that's sufficient to account for it's a sufficient axiomatization of consensus, at least as we consider it in terms of Casper. So, actually, I was delighted to hear about this last finalized thing, because that is another piece of it's more consistent with the axiomatization that I'm considering. You need this kind of what I would call like a monadic observation boundary. There's stuff. There's a boundary that you have to be able to establish. So and that's what this justification is providing. So I'm happy to hear about that argumentation. Hopefully, I can complete my deep dive on the construction, so I can talk a little bit more about the proof. But right now, I have to kind of absorb the axiomatization a little bit more fully before I can complete the consensus interpretation. That's my update.
Cool. I have a question about including information about your last finalized block in a message. Would that allow people to suss out your fault tolerance?
Yeah, this is one of my concerns. I wrote somewhere, some like notebook where I wrote like, oh, does it make sense to lie ever and kind of like change? Don't know the answer. I do think it kind of gives other people a perfect view into your fault tolerance, but I don't know. I feel like Vlad would have thought of that, but we should bring it up with him.
Yeah.
So how vulnerable is one if people can see your fault tolerance?
So I guess so. Well, let's think about it like this. In Casper, the finality gadget, like Vitalik's Casper stuff, everyone knows everyone else's fault tolerance. Right?
Yeah,
It's exactly 1/3.
Yep, that's right.
But in Vlad's kind of, at least one of the arguments he seems to make is like not knowing other people's fault tolerances makes it harder to cause, safety failures that are a big deal.
Well, and you don't have a focal point around cartelization. I think this is one of the big things he says.
Yeah, but I guess maybe you would in this case. Maybe if you kind of knew.
Yeah, if you know everyone's fault tolerance, then
right, and that's why I brought it up, is that I think you lose some of that argument, and it's strange. You can change your fault tolerance over time, right? So that you can kind of, I don't know. It's a strange thing that you can start kind of manipulating to. It's a strange signal you can send to people, and I don't know the full implications of what other people can do with that signal without thinking about it more.
Yeah, we should ask him. Greg, question.
yes.
I've heard the term trace monoidal thing a lot. But I don't. Wait, is there anywhere like I can even read like an introduction to what that might mean? Is there any R-Chain documents?
Yes. Yeah, there's tons and tons. There's lots of tutorials now on Archive. I'm on my phone, so it's hard for me to type up a bibliography, but I can easily. Is there like a Casper wiki or something? I mean, there's the R-Chain Casper wiki, but if there's like a Casper wiki, I can put up the bibliography there, or I can just put it up on the R-Chain Casper wiki, whichever one is easier for you guys.
Cool. Yeah,
I mean, you can drop some links in the that CBC Casper R&D Discord channel. Are you in there?
We can catch up later.
Yeah,
we can catch up later. I mean, I can give you a really quick account. So, I mean, you've read Vlad's Casper CBC paper, so you kind of have an idea what the category is, yeah?
Mm-hmm.
Okay, good. So then you can talk about, you can kind of generalize the idea of a product. So a product is a kind of categorical construction where you've got you've got this object that's ultimately representing a kind of pairing operation, but it's more generalized. So you can think of it as kind of a hero and contenders, right? So the hero is the product construction, and the diagram is out of the hero, you have to have the two projections into the components, yeah. And then for a contender that also has projections to the components, there has to be a unique map down into the hero, right? So that's essentially your product construction. It's just for categories, it's generalizing this idea of pairing, right? Because what pairing does is it gives you it tuples up the components, and so the natural way to think about it is to be able to decompose the elements to project out of the tuple into each of its components. So a monoidal thing. Thing general. Go ahead.
So like the hero itself is an object.
The hero is the hero is an object
with
which is
with like arrows to its elements and back.
Yeah, that's right. So the traditional example using set theory is you've got a set
Elements
of pairs. Well, no. So you've got a set of pairs, right? And then the left side projection is just the left side, the set of all the left sides of the pairs, and the right projection is the set of all the right sides of all the pairs.
Oh, cool. Okay.
Yeah. So it's pretty obvious, but you can do it much more generally. And Mike does a really nice presentation of the product limit in the Archain Retreat. He goes and that's captured on film, Christian film that. So you can look at that. So now the monoidal thing is really, it's just a generalization. So it relaxes. So you compare, but you don't necessarily have projections out. So every product is by necessity a monoidal gadget. But there are more things that are monoidal gadgets. So you can think of a tensor product, for example, as monoidal, and there's not necessarily a good, clear projection out of that. So really, it's a kind of the case where it's been used a lot recently in computer science is to model linear logic, where you're modeling the tensor of linear logic to model this monoidal use the monoidal construction to model the linear tensor product is the way to think about it. So it's a kind of it's linear in the components, and that's a lot of the that makes a lot of sense in blockchain land where you're trying to keep count of resources. So linearity with respect to the tensor product is helping you keep track of resources. And the other way to think about it is if you're aware of a monoid, then this is kind of like the generalization of a monoid. So whether you think about it as a generalization of a product or generalization of a monoid operation, both of those intuitions will get you there. Is that making sense?
Yeah.
Cool. So then the trace, what the trace does is it allows you to give, it's a feedback operator. So it allows you to loop out a construction. Like think about, are you guys familiar with the fold operation?
Yeah.
Yeah, like in Haskell or OCaml or something, or Scala. Fold is a way of doing a kind of generalized accumulator. So you could think of the trace as like a generalized fold. So it's essentially, it's looping around some condition check until you finally have an exit condition. And the intuition here with respect to consensus is you think of the message flow around blocks or the construction of common views, the sharing of views as that loop. So think about it as, imagine a Casper that just has two validators. So, while there's sort of contention over some fork, they're kind of sharing messages, not contention, but possible contention. While there's possible contention over some fork, they're sharing messages until things kind of shake out, or there's an honest to God fourth, right? One goes one way and the other goes the other way. And that's why the trace is partial, right? So if the trace were total, then it would say that they always come to an agreement. But in the presence of FLP, you've got to have situations where they can diverge. Does that make sense?
Yeah. Surprisingly,
sweet.
Does.
So basically that's all that's going on. So we're extending the trace, and so one of the best tutorials for this is Hagverdi's linear combinatory algebras. So if you look there, he gives the axioms for the trace, and then he gives lots and lots of examples of the construction. And so you can see it for sets and partial injective functions. And when you look at the traced composition, which is what this is all about, this all comes down to building a composition that has a trace around it. So when you plug the two validators together, they share messages back and forth until, in the case where there's always agreement, until they come to an agreement. And we're relaxing it to account for partiality. So sets and partially injective functions is one example. And if you look at the way the trace works, it's exactly getting the functions to agree on values where the domains overlap. And then the same is true for relations. So there's a similar construction for relations, and then there's another construction for probabilistic relations. And in each of these cases, you can kind of see, you can interpret it in a distributed way as message flow, as opposed to just straight up argumentation. Straight up injection of arguments into some kind of process. So those are really, really good examples to shore up your intuitions. And then the nice thing is that once you have it at this axiomatic level, then you can kind of lift Casper. So you could build a quantum interpretation of Casper just for fun.
Cool. Thanks for the intro. That was super awesome.
Yeah. Thanks for asking. I'm always happy to dig into that stuff. I'm gonna ring off early because my network is spotty and I have to stand in a busy part of the street in order to get network. But
I think we're good to go.
Cool.
Awesome.
All right. So I'll see you guys next week, if not before.
Sounds good.
Okay, great. Have a good one, guys.
Ciao.